High precision magnetometers are used to detect magnetic fields in applications covering navigation, space and aerospace, and biomedical monitoring. The trouble is, they're not always easy to work with given their large size and the extremely low temperatures required to operate them. But now, a new chip scale magnetometer could offer the same high precision readings in an ultra compact form while operating at room temperature. In December's issue of the journal Optica, researchers detail how silicon photonics and a unique magneto-optical material advanced this breakthrough. Paolo Pintus is an associate professor at the University of Cagliari in Italy and a project scientist with UC Santa Barbara. He is also a co-principal investigator for this study. Through our partnership with the journal Optica, in this unique episode of All Things Photonics, we're taking a closer look at the potential for this on-chip magnetometer and talking about what can be achieved when you assemble some of the brightest minds in integrated photonics, magnetic materials, and quantum studies. That conversation is next.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
Welcome to a special episode of All Things Photonics. Together with the journal Optica, we're bringing you in-depth interviews with the minds behind the latest technological advancements, pushing the boundaries in optics and photonics. It's access you'll only find here as Optica and Photonics Media team up to provide you with insight on industry-leading achievements in lasers, optics, imaging, metrology, and sensing. Joining me today is Paolo Pintus, Associate Professor at the Physics Department of the University of Cagliari, Italy, and Project Scientist at UCSB. Paolo, thank you so much for joining us today.
Thanks for inviting me for this interview.
Yeah, and excited to talk about this. But before we get into this latest study from the Optica Journal, can you kind of give me a basic overview of magnetometers and the applications that call for the measurement of magnetic fields?
Yeah, sure. So magnetometers are devices that are used to detect magnetic field, and this is not the only application. So you can have a magnetic field that can help for geolocalization, sensing, biosensing, and space exploration. So those are the basic, a few of the applications that where detecting a magnetic field is needed. And there are several devices that are been realized to detect a magnetic field using superconductive quantum interference devices like SQUID that operate at very low temperature or nitrogen vacancies. But currently, these devices are limited in size, or the apparatus to detect the signal coming from this sensing part can be pretty large, or they operate like SQUID at very low temperature. So there is a need to find smart solutions that are small, tiny, light, and also consume low power and can be used for portable application like navigation in a drone or in small devices.
And I'm very excited to talk about kind of overcoming those kind of issues that exist with the current ones and the temperature and everything like that. But before I get there too, I want to ask about the opportunities to deploy these instruments. How have they increased, and what are the applications driving the need for this technology?
So when we talk about magnetic field, we think about the magnetic field generated by the Earth, but there are other systems that generate magnetic field. For example, the activity of our brain or our heart. So we can use detection of magnetic field for monitoring the activity of brain and heart together. And there is another driving application, which is the area where GPS stop working and the signal is unavailable. For example, we think that the magnetic field generated by the Earth is homogeneous and equal all over, but it's not the case. So there are very tiny variation on the surface of the Earth due to different rocks or perturbation, thickness of the Earth's crust. And if you know and have a map of this tiny variation on the surface, we can localize yourself. You can say, I'm in this area of the globe or in another area. So if you have a device that can tell you the intensity of the field point by point, you can localize yourself and then replace the GPS signal, basically. And this is very useful for application where, like in a war environment or in area where there is a lot of signal and detecting the GPS can be challenging.
Yeah, and that's another thing we've seen in the news recently, some GPS spoofing or jamming, and we will get to that because I think it's very relevant, and we've seen cases of that happening. But before we get there, I want to talk about the heart of this breakthrough in the Optica journal. Your team managed to develop a highly precise magnetometer and to put it on a chip. What are the challenges of making this chip-based, and what materials made this possible?
Yeah, the material is the main challenge for our application. We use a material, which is a class of material, which is called magneto-optic material. So those material are sensitive to an external magnetic field, and when the light propagates through them, the material can alter the amplitude, the phase, or the polarization of the light. So to fabricate this device, we need different expertise, integration, and also material expertise. And we benefit of the collaboration with Professor Yuya Shoji from Institute of Science in Tokyo, which developed this material, and also Professor Caroline Ross from MIT, which is developing and improving new material, which are magneto-optic. Exactly. I think the most interesting part of this work was combining different expertise, like not only integrated photonics, but also the magnetic material aspects, and also the quantum aspect in order to improve the efficiency. That's something that I really enjoy, interacting with different expertise.
Interesting. And reading in that study, I believe the material is called cerium doped yttrium iron garnet. Very interesting. I don't know a lot about this. Tell me a little bit about this and what this kind of material has given you guys access to accomplish.
So the benefit of this material is being transparent and 1550 nanometer, which is the wavelength used in optical fiber communication. So it's compatible with a standard telecom system and is traditionally used for fabricating integrated isolator and circulator, which are a special class of optical devices. So the recipe of this material has been optimized by Professor Yuya Shoji, as I mentioned before. And at UCSB, we take this material, we bond on top of an integrated interferometer fabricated in silicon photonics, and we leverage this property of varying the permittivity and the refractive index to being able to detect an external magnetic field.
Very interesting. Now, this material, is this something that was hard to come by? I know you said the associate professor from Tokyo was able to help give access to this. Is this something readily available, or how hard is this to obtain?
Well, there are different class of magneto-optic material, but they are not really used because uh, having magnetic material in a silicon foundry is not ideal. So that's why we need to take the expertise from another group which has developed this material, and we perform bonding instead of direct deposition for several reasons, avoiding contamination and having a very good material quality.
Very interesting. And you mentioned before a little bit, and we're going to talk about now. Magnetometers typically operate at extremely low temperatures. Talking 0 Kelvin, which I imagine presents challenge to get them there. And this chip scale magnetometer uses light for high precision magnetic sensing, and it can be done at room temperature. How did you guys accomplish this, and what does that mean for the future applications where temperature may have been an issue?
Well, this is actually one of the key features of this material. This material is sensitive to an external magnetic field at room temperature, so we don't need to cool down the sensitive part. And this is not actually a limitation because there are a class of magneto-optic material that operate at low temperature or higher temperature. So having material that can be selected according to the working temperature is extremely beneficial, and allowed us to avoid any cryostat or complex apparatus to keep the system cold, and also the power consumption that is needed when this cryogenic system, and also connecting the system and packaging the system that has to operate at very low temperature. So this is an extremely benefit of this proposed solution.
Very interesting. And we always know when you can increase the flexibility of something, you can, open it to more applications when you are no longer restricted by those hurdles. And in what way is this work a silicon photonics breakthrough? And in other words, how have breakthroughs in that material platform enabled this current advancement?
Well, it's a breakthrough because this class of material has been mainly limited for optical isolator and circulators. So has been seen like a very niche field in the photonics area. So exploring a new application, so magnetic field sensing in a integrated optical device is definitely a breakthrough. But it's not the only one. With our collaborator, we explore other applications. So, for example, integrated magneto-optic memories for optical computer. This is an activity that we carry at UCSB in collaboration with Professor Nathan Youngblood from Pitt's University. Or we explore also magneto-optic modulator for data link from cryogenic to room temperature. So I mentioned this device operates at room temperature, but can operate also at cryogenic. So exploring different areas beyond optical isolation, which span from sensing, communication, and computing, is definitely the major breakthrough of integrating this material in silicon photonics chip.
And putting this on a chip, what can that mean for the future of space missions or even biomedical applications?
Well, for space mission, one of the main challenge is the payload. Every time you send something in space, you have to be very careful what you are sending in terms of weight and energy consumption, because your battery are limited and you cannot consume too much fuel just to carry all the instrument in space. This device is extremely small, like few millimeters square. The weight is a few grams and can consume roughly less than 100 milliwatt. So this is a strong benefit for this class of, for this kind of application. And for biosensing, the main benefit is not definitely the sensitivity. There are higher there are other other magnetometer which has superior sensitivity, but is very small compared to them. So you can integrate many of them and have a better and larger map of your magnetic field in a small area.
Very interesting. And we mentioned before about GPS and issues there, because it wasn't long ago I spoke with someone on this podcast about laser communications and overcoming situations of GPS jamming or spoofing. And we're seeing that in the news with some stuff over the Baltic and some claims from what Russia may be doing. I don't want to talk about specific situations, but how could this advancement really advance navigation tech?
Yeah, as I mentioned before, you can use the micro variation and on the surface of the Earth, and the micro variation of the magnetic field, and to localize yourself. So some area have different rocks, and the rock have different geological history. So knowing the magnetic field variation, you can know exactly where you are moving along the surface of the globe. So that is the way you can avoid using GPS and using an alternative solution.
So this kind of navigation tech would not rely on any sort of satellites, just kind of reading magnetic field and what's around it.
Yeah, exactly. Instead of checking what is on top of you, like GPS, you have to look what is under yourself on the surface of the Earth.
Very interesting, and something that would be much harder to interrupt, right? Because it's, you can throw up signals in the air, but you're not going to change the magnetic fields around you.
Exactly. And for this kind of application, the payload is very important. For example, imagine that you have to drive a drone or a small airplane. So if you have something which is big and you have to pay a price in terms of energy consumption and the area and the volume that you occupy, if you have a very tiny device, it's much easier to incorporate this device on your system.
At Photonics Media, we're very familiar with laser light and its applications. But when I was reading this study, I saw that this magnetometer can operate at higher performance by injecting quantum light, and that term stood out to me. What can you tell me about quantum light?
So our device is based on an optical interferometer. So it is integrated in a small size, but it's still an optical interferometer. So we take advantage of the phase variation in order to detect the magnetic field. Now, light has an amplitude and has a phase. And when you consider tiny variation of amplitude and phase, you cannot consider those as a continuous variation. But there is a sort of, there is exactly an uncertainty principle behind that. So you can assume to squeeze the phase, so have high precision in phase, and neglect the precision in the amplitude in order to have a better accuracy in the detection of the magnetic field. This idea is not new, has been used for improving the accuracy in other kind of optical interferometer, like in gravitational wave detection. And what is new is integrating this idea on a single chip. And we are benefit of the expertise from Professor Gallant Moody from UCSB, who is an expert in a quantum device and is working on improving the squeeze light production in order to increase the sensitivity of this class of device. In this case, is a magnetometer, but it could be any kind of sensing where you need to detect with high accuracy the phase variation in your device.
And let me ask you in closing, where would you like to see this technology being put to use, say, 5 or 10 years from now? What applications do you think this could make a real impact in advancing applications?
I think navigation is probably one of the most, because navigation and space exploration, the kind of area where the payload is very important. Putting a tiny magnetometer in a spacecraft is very interesting, and people from NASA, ESA, JPL Lab, we interact with them when we were writing this proposal, are very interested, but usually those devices are pretty large and heavy. So I think this is probably the most immediate application of this kind of device, considering also the current sensitivity of this device and the dynamic range. Application like biosensing is definitely something interesting that where our device can be used. The main limitation is the current sensitivity. The magnetic field generated by the brain, by the heart, is very small, and by the brain is 2 or 3 order of magnitude smaller. So we need further investigation, probably consider alternative solution, alternative material, not just cerium gig, but material with better performance in terms of and better sensitivity to detect such a tiny field.
Paolo, thank you so much for giving us the time and sharing more about this study, and we're excited to see where it goes.
Thank you for inviting.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.